speaker is Akshat Mudgal from Bristol and Purdue, who speaks on additive energies on spheres. So please.
Firstly, I'd like to thank the organizers for organizing this very nice conference and for giving me an opportunity to give a talk here. And today I'll be talking about additive energies on spheres. So let's begin by seeing what kind of spheres we'll be studying in this talk. So given some natural number m, I will be considering the sphere in 4 dimensions of radius square root m, and in particular, I'll be considering lattice points on it. So, and I'll call this the discrete sphere or the sphere SM. So these are the integer points which satisfy this equation. And here I'm using this vector notation. So whenever I have a bar below an x, it just means it's x1, x2 till x4. And what I want to do in this talk is I want to study additive properties of elements of SM. So given a set of lattice points which satisfy this equation, I want to know what are the additive properties of the set. And so given an arbitrary subset A of SM, so A is just some finite set of these lattice points, and given a natural number S, I want to look at the S-fold additive energy of A. So this is the S-fold additive energy. And what is this doing here? So basically we look at the equation A1 plus A2 till AS equals AS plus 1 till A2S, where all the variables are now lying in my set A. So all the variables are vectors and each such vector lies in my set A. And this is the S-fold additive energy. This is quite a common topic that is studied by additive combinatorialists and analytic number theorists. And we want to study estimates for the additive energy of A when A is a subset of the sphere. So perhaps before getting into talking about what bounds we know for the additive energy, maybe I can briefly talk about why should you care about the S-fold additive energy. So why should you study the S-fold additive energy?
Nie, to chyba pytanie do ciebie.
From a number theoretic perspective, this is equivalent to studying a system of Diophantine equations. And to sort of see this, you can just take A to be the whole set SM. In that case, you can see that this equation is actually a system of 4 linear equations because each such vector has 4 dimensions. So these are 4 linear equations in these many variables. But moreover, each vector lies on the sphere. So each vector here satisfies an equation of the form x squared till w squared equals m. So you have 2s quadratic equation. So this simple looking equation is actually a combination of 4 linear equations and 2s quadratic equations running through 8s variables. So studying estimates for additive energy is equivalent to studying this complicated looking system of Diophantine equations. And moreover, it turns out that the additive energy is a very nice measure of additivity. And in turn, if you have bounds for the additive energy, you can control various other additive measures. For example, there is something known as lattice point correlations, which is studied by people who are interested in the topic of arithmetic random waves. And to get estimates for lattice point correlations, it suffices to bound additive energies. So it sort of plays a nice central role in understanding the additive properties of elements of SM. And moreover, estimates for this additive energy not only have number theoretic motivations, but in fact, this problem lies on the interface of 3 distinct fields of math. So the second motivation comes from harmonic analysis. And maybe I can motivate this by mentioning the following expression. So it turns out the S-fold additive energy can be written as the following mean value. So you look at an exponential sum where all the variables are running over your set A. Remember, A is a set on the sphere. And you look at this exponential phase, take the 2s moment. And you have this expression simply because if you unpack this and apply orthogonality, you precisely pick out the additive quadruples or 2s tuples. And because we have this expression, it turns out that if you're studying additive energies, they actually give rise to what are known as discrete restriction estimates for lattice points on spheres. So in particular, if you plug in some weight here, you can imagine this to be some extension operator on a sphere, and harmonic analysts are interested in understanding how the 2s norms of this exponential sum behave in terms of the applied weights. So it's quite closely related to this quite popular topic, actually. This topic surrounding discrete restriction estimates for curved surfaces has seen a lot of major progress in the last decade, coming from the decoupling results by Burgundy, Meter, and Guth, and the efficient congruencing work by Trevor. So it connects to some popular topics quite nicely. And moreover, this exponential sum here, these are actually connected to eigenfunctions of the Laplacian or the four-dimensional torus. So again, I mean, there's this sort of a arithmetic random wave connection about with these mean values of exponential sums. The last connection that I'll be talking about is the one which is the most straightforward in some manner, and it's about connections with incidence geometry. And to highlight the connection, maybe I can just consider the case when s equals 2. So when s equals 2, I just want to study all the additive quadruples of this form where a1, a2, a3, a4 lie on the sphere. But whenever you have such an additive quadruple, you can note that the point a1 plus a2 lies on the translate of the sphere a3 plus sm. So whenever you have an additive quadruple, that actually leads to some sort of an incidence between a point and a translate of a sphere. And so if a1, a2, a3 are varying across the sphere, then what you have here is you get a point set of this form, you get a set of translates of the sphere of this form, and you're basically measuring how many incidences do I have between this point set and this set of spheres, which is a classical sort of a problem that you'd study in incidence geometry. So this problem lies on this intersection of these three distinct areas. And it's actually supported by the fact that most of the progress that has been done on this problem has derived techniques from all these three areas. So I hope I've motivated this problem fairly well. And now let's get to seeing what kind of estimates that we know for S-fold additive energies. So let's see. So what are the known bounds and heuristics for additive energies? So maybe I can mention the most trivial bound. This was also mentioned in Peter Bradshaw's talk on Monday. It is that given any set A in RD, the additive energies are bounded by size of A to the power 2s minus 1. Here, this just means the cardinality of A. And they are bounded below by size of A to the power s. These are incredibly trivial bounds. To sort of see why they exist, you can just look at the twofold case. So to get the lower bound, you can just imagine I can let A1 be anything, A2 be anything, and then I can simply put A3 to be A1, A4 to be A2, and I'm done. So I get these A to the power s diagonal solutions, where the solutions are a permutation of each other. And to get this upper bound, you say, okay, let A1, A2, A3 be anything. And once they're all fixed, A4 gets fixed because of the additive equation. So you fix 2s minus 1 of these guys, and that's a trivial upper bound. Here I'm using Vinogradov notation. Basically, I'm hiding some implicit constant that's an absolute constant. And moreover, this is something that I'll use throughout the talk. Whenever I have an epsilon on the Vinogradov notation, I just mean there's a constant that depends on epsilon, but this is true for all epsilon greater than 0. So specifically for epsilon, I just mean to say that this is true for all epsilon greater than 0. Anyway, so you have these really trivial bounds on additive energies, but here we haven't used any facts regarding spheres. So the question is, can you do better if you assume that A lies on the sphere? And in fact, you can. So suppose M is odd, just for the moment, let's suppose that, and suppose S is greater than 2, then the additive energy, the S-fold additive energy of the whole sphere is at least the size of the sphere times 2s minus 2. So in fact, this is pretty cool because we can really see that we are much closer to this upper bound than this lower bound. And maybe I can provide a quick, nice proof that will also illustrate why we get the bounds that we get. So the proof is quite nice. You just begin by noticing that if X lies on the sphere, then all the coordinates are actually bounded. So when X lies on the sphere, all the coordinates satisfy this, but in particular, this implies that each individual coordinate must lie in this box, just by considering the sizes. But what this means is that the whole sphere SM is contained in this four-dimensional box. And these are super trivial bounds. I haven't done anything. But now what I can do is I can consider S-fold subsets of the sphere. So, I mean, just to refresh this notation, S-fold sum set of any set simply means I take all possible S-fold sums that can arise out of the set. So I'm just looking at all possible S-fold distinct sums. And since you have this containment, we can actually see that the S-fold sum set must also be contained in just a slightly larger box. And in fact, this containment allows us to immediately see that the S-fold sum set must in fact be quite small. So the size of the S-fold sum set must be bounded above by the size of this box, which is some implicit constant depending on S, I don't really care about that, times square root m to the power 4, which is m squared. So I can see that as S grows large, I have a very good bound for the S-fold sum sets of the sphere. And now I can use the fact that m is odd. So a classical estimate and analytic number theory says that whenever m is odd, m has a lot of representations as a sum of 4 squares. So in fact, we have the following upper bound, that m squared is bounded above by sm squared. And now a standard idea in additive combinatorics tells you that if you know something about the sum set, you can usually transfer that to additive energies. And this is the more easier version of that. So Cauchy's inequality allows you to discern that the S-fold additive energy of the sphere is bounded below by this size of the sphere to the power 2s divided by the size of the sum set. And just plugging these bounds back in, I get that this S-fold additive energy must be exactly as large as I mentioned. You should have the 2s minus 2 bound here. So this sort of tells us some of the numerology that we expect to have a 2s minus 2 here. So now the question still is, so we have these lower bounds, but is 2s minus 2 the right exponent, or is the upper bound 2s minus 1 the right exponent? And it turns out we believe we should be much closer to this bound. And I can explain this heuristic as a part of a more general phenomena known as the discrete restriction conjecture. So in 1993, Burkan studied the discrete restriction conjecture for lattice points on spheres in 4 dimensions. And Burkan basically conjectured the following. So suppose that you have any set of complex weights, any sequence of complex numbers. Then if you look at the if you look at the capital L4 norm of this exponential sum, so again, this should remind you of something that we wrote previously. When ANs are 1, this is just the twofold additive energy. So Burkan was studying these because of their connections to eigenfunctions of the Laplacian on the torus. And he conjectured that the L4, you should have some sort of a square root cancellation for this exponential sum for this mean value. And so this L4 norm should be bounded above by the L2 norm of the complex weights, times maybe an m to the power epsilon loss as a careful factor. And you can already imagine, because of this expression of S-fold additive energies as mean values, you can imagine that this should somehow give us a conjecture for additive energies. And you'd be very correct in thinking that, so maybe I can just derive it here. So given a subset A of Sm, what we'll do is we'll simply set An to be the characteristic function of A. So this is 1 when n is in A and 0 elsewhere. And now I can apply orthogonality. So if I set this value of An in this above exponential sum, and I unpack this 4th power and apply orthogonality, I simply see that this inner thing turns into the twofold additive energy of A, whole to the power 1 by 4. And then the discrete restriction conjecture tells me that this is bounded above by m to the power epsilon times this L2 norm of the weights, and then plugging the weights back in, I get this is A to the power half A. So in particular, we expect that the twofold additive energy should be bounded above by this m to the power epsilon factor times A squared. So in fact, we really expect that if A is a set on the sphere and A is somewhat large, then you really expect it to be almost Sidon up to this m to the power epsilon factor. And maybe I can quickly mention that despite this amazing progress that has happened in the past decade regarding discrete restriction estimates, this conjecture is still open. We don't know whether this holds true or not, even in 4 or the analog in 3 dimensions. So there's still a lot of scope for major work. And maybe, we just studied the twofold case, but people in analytic number theory and additive combinatorics will realize that this is good enough to give us upper bounds for the S-fold additive energy. So simply using some basic triangle inequality, I can see that the above bound implies that for all S-fold energies, whenever A is a subset of the sphere, you should have this bound. Maybe I can just call this star. And maybe,
So,
sorry. Okay.
thank you
Maybe
very
the
much.
last,
Let me see if there are any questions.
uh, don't I have 10 more minutes?
Oh, I'm sorry. Yes, yeah, no. I continue. I'm sorry. Please continue.
Oh, okay. Well, I can maybe quickly
At
mention.
least 10.
We use the discrete restriction conjecture, which is still an open conjecture, and we use this to get stars. So we showed that if discrete restriction conjecture holds, then you get these bounds on additive energies. Well, it turns out a standard heuristic in harmonic analysis known as restricted interpolation, in fact, implies that these are equivalent. So if you want to study this much more harder conjecture, well, it suffices to just study additive energies. And then somehow using some dyadic arguments, dyadic decomposition type arguments, you can ensure that these weights can simply be replaced by characteristic function of sets. So the conjecture, these upper bounds on additive energies are equivalent to the discrete restriction conjecture for lattice points and spheres in 4 dimensions. So with all these conjectured estimates in hand, maybe we can start looking into what is known for this problem. So we expect S-fold additive energies to satisfy this bound. We expect to get an a to the power 2s minus 2 here. And in fact, in 2015, Burgan and Demeter proved the following bound. So they said that whenever A is a subset of the sphere, the twofold additive energy is bounded above by m to the power epsilon times a to the power 2 plus 1/3. So we expect an a squared here, and the trivial bound is a cubed, and they managed to get a 2 plus 1/3. And as before, using this simple triangle inequality type stuff, you can get that the S-fold additive energy should be bounded above by a to the power 2s minus 2 plus 1/3 from their result. And this is quite nice. This gives you a power saving, but you can still see we are an a to the power 1/3 away from the conjectured estimate. And maybe I can also mention what are their proof ideas, because this might be interesting to some people in the audience. So Burgan and Demeter used point hyperplane incidences in R4. They in fact use a very clever idea to reduce these additive energies into point hyperplane incidences. And so since they use these purely incidence geometric arguments combined with some very basic number theory, this can be seen as some sort of a threshold bound. The more interesting aspect of the result is that this also holds true if you replace the spheres by paraboloids. So I'm going to quickly define the truncated paraboloid, which is going to be a curved surface of this form, where the first 3 coordinates are between minus m and m. And so you have this nice sort of a truncated paraboloid kind of thing. And the restriction theory and incidence theory for paraboloids and spheres are supposed to be very similar. And in fact, this is further evinced by Burgan and Demeter's bound, because they mentioned that theorem 3, that is their theorem, holds if A is a subset of the paraboloid as well. So the arguments run precisely the same way if A is a subset of the paraboloid. But here is where things get even more interesting. So by a simple calculation, as we did before, you can see that the additive energies of paraboloids are actually do satisfy 2s minus 2 plus 1/3. So using purely incidence geometric ideas, you could never hope to do better than these 2 bounds, because they are sharp when you consider the case of paraboloids. And incidence geometric methods, as in Burgan and Demeter, will work essentially mutandis for paraboloids. And they said to go beyond this. So remember, for spheres, we expect this to be an a squared and this to be an a to the power 2s minus 2. And they mentioned that to go beyond this threshold, you really need to use some fact about the distribution of lattice points on spheres and paraboloids. They are different. On spheres, you have some irregular distribution. And so our main result basically does cross the threshold. So our main result is as follows. We prove that whenever A is a subset of the sphere, then the twofold additive energy can be bounded above by a to the power 2 plus 1/3. This was Burgan and Demeter's bound, minus a positive constant C for some C greater than 0. So we are able to go beyond this threshold that was set by Burgan and Demeter. Moreover, We could again interpolate this to get bounds for S-fold additive energies by simply saving a 1/3 minus C. But we can do a bit more using more incidence geometric techniques. We're able to show that the S-fold additive energy is bounded above by a to the power 2s minus 2. This is sort of the conjectured bound. And we get a plus 1/6 here and something that goes to 0 as s goes to infinity. So in some sense, we get a to the power 2s minus 2 plus 1/6 plus some eta s, where eta s can be made as small as you want as s becomes appropriately large. And so we can see that the results of Burgan and Demeter, which gave a to the power 2s minus 2 plus 1/3, I mean, we can really go from 1/3 to 1/6. And the conjectured estimate is 2s minus 2. So we are 50% closer to the conjectured bounds. Well, almost 50% closer, 50 plus epsilon % closer. And perhaps I can now quickly mention some of the proof ideas. So as I mentioned before, this bound does not hold for paraboloids. So our method is able to differentiate between the case of spheres and paraboloids. And so we need to use some sort of number theory. The people who work in incidence geometry and additive combinatorics know that whenever you have to get a threshold breaking bound, you should maybe think about using the higher energy method. Because often incidence geometry is very good, well, at least Semery-Trotter is very good at giving you bounds on higher energies, and then you can combine this with the higher energy method of Shkredov and Schoen to get these threshold breaking bounds. Well, it turns out while Semery-Trotter is nice with higher energies, the higher dimensional incidence geometry is actually pretty bad with higher energies. So in fact, if you use a combination of incidence geometric ideas to get good bounds on higher energy, maybe I can quickly mention if you look at this higher energy. So this might be familiar to people who, for example, work on additive energies on convex sets. The bound, the trivial bound is a to the power 4, but the bound that incidence geometry gives you in this case is a cubed. More like m to the power epsilon a cubed, but whatever. And this is quite nice, but it's the additive energy bounds that it gives you along with the higher energy method look like m to the power epsilon plus a to the power 2 plus half. And we can already do much better simply because we have 2 plus 1/3 from Burgan and Demeter. So just blindly applying higher energies will not give you anything in this problem. And could you do better than the a cubed? Not really, because you have these sub-varieties in some sense living on this equation. So you can simply put x1 to be minus x2, x3 to be minus x4, x5 to be minus xs, and you generally see that this a cube factor is short. So because of these sub-varieties, you can't do better by simply applying the higher energy method. So the proof in some sense goes as follows. So you write A as X union Y, where X is a non-arithmetically structured set. So X will have bad additive properties and Y will be arithmetically structured. Like it will have some nice additive properties. And it turns out when X is not additively structured, I can now apply incidence geometry. And so I get some ideas from the point hyperplane methods of Burgan and Demeter, but I also have to plug in point sphere incidences, which is sort of a new idea into this kind of a problem. And using a combination of these two incidence geometric methods, I can get good bounds for the higher energy, only in the non-arithmetic case. And then I can apply higher energy and some other combinatorial ideas to get threshold breaking bounds for X. Now, how do we deal with Y? Y is the more arithmetically structured side. Incidences don't really work for Y. Well, in this case, since we are working with a geometric problem, arithmetic structure is often closely related to geometric structure for this problem. And we have to use more elementary combinatorial number theoretic ideas, looking at how various three-dimensional spheres of varying radii intersect with each other in 4 dimensions and play around with those additive interactions. And maybe with that quick overview of the proof, I can say thank you for your attention.
Thank you very much. Let me ask again, are there any questions for our speaker? You can enter a question in the chat or the Q&A or raise your hand. Seeing none, I thank Akshat again for his talk. And our next talk will be in 7 minutes.